Hello, everyone. Welcome back to the AAS Journal's Author Series. And I'm super happy to have Zhuo Chen with us today. Hi, Zhuo.
Hey, Frank.
How you doing?
Nice to meet you.
Good. Nice to meet you. Where are you at?
I'm at Edmonton. I'm now a CETA National Fellow at the University of Alberta.
Alberta. And how is the summer in Alberta this year?
Oh, it's great. It's sunny and cool. And yeah, my next move is to go to in this September. I'm going to move to the Tsinghua University as a postdoc fellow there.
Well, congratulations.
Yeah, thanks.
Yeah, that's great. Little different weather there.
Yeah, it's hotter in the summer, and yeah.
Yeah, very cool. Very cool. So you're a postdoc now?
Yeah, I'm the second year postdoc.
Okay, good. Awesome. What do you like to do for research?
Currently, I focus on the radiation hydrodynamics. And so what we are going to introduce, the paper is one of my previous project, the AGB binary. And that's also one of my focus, the binary stellar evolution.
Okay.
Yeah.
Very cool. And with that, why don't we go ahead and get to it? And today, we are going to be talking about a 3D radiation hydrodynamic AGB binary model. And Zhuo, take it away.
Thank you. So I'm going to throw the conclusion and the takeaway of this paper first. So I think the main takeaway of this paper is the evolution of the closed binary, of closed binaries are poorly understood for us now. And our new model, this new model in the paper suggests that the mass transfer efficiency may increase sharply when the wind-Roche lobe overflow takes place. This dramatic increase in mass transfer efficiency can impact future binary evolution. And okay.
So I think this is also, if I'm not mistaken, correct me if I'm wrong, I think this is the first 3D rad hydro AGB binary modeling people have done.
Yeah, I think it's the first 3D radiation hydro model currently we have, and also but also the model suggests that there are new results. For example, the circumbinary disk can appear in the around the AGB binary.
Right.
Yeah, and that's previously has not been observed in other research. So consistently, yeah. So the motivation of this paper, of this research, has many astrophysical observational background. So the first and the one of the most interesting motivation is that there are many chemically peculiar stars in the universe, in our galaxy. And one of the chemically peculiar star is the S-process enhanced peculiar star. And the S-process element are usually produced in AGB star. But if they are found in the less evolved star, we can infer that they get this element from a companion, that more evolved companion, which is now maybe a white dwarf. And another interesting motivation is there are many some long-term observational campaign that has monitored the AGB binary and their eccentricity. And they found that the eccentricity is not zero for evolved binary stars, for close evolved binary stars. This is not intuitive or counterintuitive because the AGB stars are large and they are fluffy. So the tidal interaction usually can circularize the orbit within the lifespan of the AGB star for close binary. Usually this range is 6 to 10 AU. They can circularize the orbit. And however, we found, the fact is that we found many stars, evolved binary, that they have non-zero eccentricity. That means some process has taken place to pump up the eccentricity. And however, we don't have an explanation for this mechanism. And that's however, people have proposed that something like circumbinary disk can pump up the eccentricity.
Okay.
Yeah, and this paper may help to find how the circumbinary disk forms. Also, if we look at the planetary nebulae, some planetary nebulae, they have bipolar outflow. And one of the planetary nebula called the butterfly planetary nebula, which is also the NGC 16302. It has a dusty tori in the middle plane. And it also has a low mass central star, like approximately 0.6 solar mass, evolved central star. So, how does this tori come from? And we could infer that it is from through the binary evolution, from the angular momentum transfer of the binary, and it forms piles up and forms a dusty tori, dense dusty tori in the central place, and also and then the energetic outflow, fast outflow, eject in the polar direction and form the shape, the bipolar shape. We also observe many planetary nebula with spiral structures. That means the outflow is like spiraling out when we observe the velocity channel map. And that's another morphology. And these two types of morphology can be unified by this model presented in this paper. Cool. These two morphologies and can be explained by this model. And also some AGB stars exhibit UV access. And we know that usually AGB stars are very red because of the dust. But when they exhibit the UV access, we can infer that there is something accreting the mass, and the infalling mass create the UV photon. And observational evidence showed that, for example, the Sahai et al. In 2008 and Ortiz, their research have found that there are such binary systems exist. That's the observational background and the motivation of this paper. So if we go from that, we can think about the binary system and think about the astrophysics and the physics in this system. So if we go to the figure 1, and if we focus on the figure 1, and we can think about more about the physics. And this is a schematic picture of the wind rotational overflow, which is the central picture of this paper. So the HB star is indicated with a yellow color. It's a circular, it's a circle. So it fills a fraction of its inner Roche lobe, but it's not filling it to the full. And there's a secondary located on the right to the right of the HB star. So the HB star has a dust formation zone. We represent that with a gray color. The wind-Roche lobe flow take place most efficiently when the dust formation zone is comparable to the inner Roche lobe of the HB star. And this is the time when the wind-Roche lobe flow are most efficient. And in this picture, there are several important physics we need to think about. One is the dust formation. If the dust is very susceptible to many conditions, for example, the radiation, shock, or even, and also the density and the local density. So this condition determines where the dust and what species of dust form, the chemical composition and the chemical composition. So when the dust form, they can absorb a lot of short wavelengths radiation from the star, the HB star. And then this dust pick up the momentum from the photon, and they can accelerate and drag the gas around it and through the frictional force. And then the whole gas and dust mixture is accelerating outward. In a binary, this acceleration will be, this material will be deflected by the secondary, but because of the gravitation of the secondary. So when the dust formation zone is close to the L1 point, the flow can efficiently channel through this bridge, through the saddle point, and to the secondary efficiently. Also, also in other direction. And another less investigated aspect is there could be an ionization zone near the secondary. For example, if the secondary is a main sequence star, the ionization could take place just near the very inner side, inner boundary of the surface of the main sequence star. And we indicate that with a purple line. But that ionization, the ionization means that there is a phase transition from the molecular state to atomic state, and then to the ionized state. And this transition take a lot, there are binding energy, which is huge. The binding energy of this phase transition is huge, and it can affect the accretion efficiency. And that's less investigated, area, and could be some other project. And but this is could be a very interesting problem. And then let's go to the and this is the astrophysical background I want to introduce. And then we can move to the figure 2. And because the dust, it plays a central role in the mass transfer of the AGB binary. So I want to talk more about the dust. Dust, as I said, dust can absorb short wavelengths photon efficiently. In this map, in this picture, I showed the opacity, the wavelength dependent opacity of different kinds of dust. I differentiate, vary the ion concentration of the dust. and they are all pyroxylene. So we can clearly see that in the short wavelengths, for example, in the optical band, the opacity is very high, and then it drops quickly towards the 1 or 2 micron. The yellow band indicate where the K band lies. At this K band, the opacity is already very low compared to the short wavelengths, the peak of the short wavelengths.
Mm-hmm.
And we from here we understand that only the short wavelengths can be efficiently absorbed by the dust, because the power spectrum of the AGB star is indicated with the blue dotted line. So the peak of the power spectrum in figure 2, the peak of the blue line is where the peak of the power spectrum of the AGB star is. So only the short wavelengths or below the K band, wavelengths smaller than the K band, can be efficiently absorbed. And we use that to deduce something like the dust formation radii, and we can calculate how much photon can the dust absorb and how much momentum can the fluid gain. And okay.
Let me ask a question. Where do these opacities come from?
Oh, this opacity is we use mean model, and we assume that the dust has a base a distribution. So between the 0.1 micron to 0.3 micron, it obeys its radius obeys a distribution that is the same as the ISM. And the mean model can provide us the opacity if we have the optical property of the component. For example, we get this pyroxylene, we get this data from a database called the Jena dust database.
Okay.
Yeah.
Thanks.
Yeah. And so a conclusion is a summary of the dust formation radii is shown in table 1. Yeah. So we kept the second and third column shows the dust formation zone radii, the initial dust formation radii of different kinds of dust. The second column is in the second column we assume the dust radius is fixed as 0.005 micron, and the second column is 0.001 micron. They're all very, very small, and that's when initially the dust can form. And we can see that the less the ion, the closer the dust can form to the star. Can form, but roughly it forms around 2 stellar radii. The stellar radii is defined as the photosphere, so it forms roughly around that area. And okay, so this is how why that the short wavelengths, only the short wavelengths can be used to accelerate the dust and the fluid. And next, we will use this simplified dust absorption model to generate a phenomenologically pulsating AGB star and accelerating AGB wind. And the result is shown in figure 3. And
figure 3.
Oh, this is the piston model.
Oh,
sorry. This is not the result, but this is the where we place the piston of the AGB star. So we need a piston to perturb the bottom of the our boundary, and then this piston can drive shocks into the upper atmosphere of the AGB star. And when the shock propagate to the radii that we have mentioned, like around two stellar radii, it dust can form, and then it can accelerate, can be accelerated, and then it can the fluid, the gas can continuously move out. And this is the location of the piston, and is placed at 247 solar radii. And the table 2 summarizes some of the parameter of the AGB model we use. And for example, the photosphere is at 269 solar radii, but the piston is below the photosphere.
Right.
And the effective temperature is 2,874 Kelvin. And also we have this the density and temperature of this piston. Note that the effective temperature is much lower than the piston temperature because the piston is below the photosphere. And so when the piston, the gas come out from the piston, it can be cooled down. That's why we also need a cooling algorithm, a cooling mechanism to cool the gas when such that it can drop, its temperature can drop below the dust sublimation temperature.
Yes.
And next we can present the AGB star model, and it's in figure 4. Yeah.
Okay.
Yeah. So the first panel shows the single star AGB star, the mass loss rate and the piston velocity of the single AGB star. The black solid line is the mass loss rate measured at sphere that is very outside. And we can see that since the piston has a 1 year period, the blue line is the piston velocity. And we need to look at the secondary y-axis. It's sinusoidally varying. And so the piston gas is accelerated outward, and then when the dust form, a steady flow. But because we have piston there, it's also a periodic wind. So the mass loss also varies accordingly to the sinusoidal piston model. And its mass loss rate ranges from 2 to 4.5 times 10 to the minus 7 solar mass per year. And then the second figure shows the profile of the AGB wind, the velocity profile. And the x-axis is the radius from the center of the star to 16 AU. And the right axis is the velocity. The blue line in the second panel is the escape velocity, the local escape velocity to the star. And the yellow zone is the AGB star, the interior of the AGB star. The boundary of the piston is located at the boundary of the yellow zone. And we also indicate the dust formation zone with a gray color. And this is consistent with the first figure we use. The color is.
I have 2 questions.
Yeah.
The one, this is still the 1D model. You have a map that's into 3D yet, right?
It's 3D. It's 3D.
This is the 3D model.
It's 3D. Yeah. So the mass flux, the first figure, the flux through the sphere is sampled at in 3D simulation at 10 AU radii.
Got it.
Yeah. And
Okay.
yeah, it's a summation through a sphere.
Got it.
And this okay, the second panel is the velocity map, and we see that there is fallback between the stellar piston and the dust formation zone, because before the dust form, the opacity is still very low, and the radiation cannot always drive the gas outward. So some of the gas can fall back when shock just pass through. A shock pass through, and then the material behind the shock will fall back because there's not much momentum in the gas. And so in between the dust formation zone and the piston, the gas is constantly going out and falling back.
Right.
And the third panel is we place a test point to record the time variation at 2.75 AU, and that's already outside the dust formation zone. Yeah, that place is is right in the dust formation zone. Yeah. So we record the density variation with time, and also the temperature variation with time. And we can see a phase difference because the shock will increase the density, but also the front of the shock is heated, and the behind the shock, the temperature is lower, and but the density is higher. And this is a illustration that we can use this simplified dust formation model to create a phenomenologically pulsating AGB wind. And from many aspects, the AGB wind meet what we observed in the in observational astronomy. For example, the mass loss rate is usually 3 × 10⁻⁷ for such AGB star, such kind of AGB star. But the terminal velocity, the wind terminal velocity in our model is roughly 14 kilometers per second. This is slightly higher than the observed AGB wind, which is usually around 12 kilometers per second. But that's not a big difference.
Yeah.
Yeah. And
so let me ask another question. How do you implement the piston in a 3D model?
So we use Astrophysical, and this is a 3D code with static mesh refinement. And we use Cartesian grid, and we set up a region that is highly refined, and we just in that region we don't care because that's inside the region, but the boundary is the piston.
Got it. I understand.
The boundary of that region is the piston, and at that place, those cells they have varying velocity, but fix the temperature and the density.
Yeah, at the piston boundary. Yep, understood. Yeah. Okay, thanks.
Yeah, and so here this concludes the 3D single star model, and we can go to the results of in Figure 3.
All right.
So this we place this 3D AGB star in a bigger box, and also place another central gravitating body around it, near it. But we vary the distance between the central gravitating body and the AGB star. In this picture, left column shows the density. The central column shows the optical depth traced back to the sphere, a boundary that encloses the AGB star. It's not a spherical boundary, but it's a contour, the density contour of something, yeah, that encloses the AGB star. The third column shows the temperature, and also the first, second, third, and fourth row shows 4 simulations that we have carried out, and with different binary separation. The red in the first column, a big red circle is where the AGB star locate. And the secondary is in the on the y-axis, just above the AGB star. So in the first column, first row, it has a 5.4 AU binary separation, and the secondary has an accretion disk around it. And also we observed a circumbinary disk form. And the secondary, the accretion disk casts a very cast a very strong shadow behind it, which can be seen in the second column of the first row.
Right.
And this shadow blocks the radiation from the AGB star. So when material that move around into this shadow, they will not experience any radiative acceleration. So they will just experience the gravitational force from the 2 stars, and they will fall back a little bit. And in the third picture, the temperature picture, we can see that there is a high temperature zone. If you can zoom in into the third column, the first row. This is second row, yeah, the first row. We can see that there is a high temperature zone just at the edge of the accretion disk. And that's a shock. That's created by the shock because the accretion disk is moving through the circumbinary disk.
Yeah.
And this is a very important layer because it's if some material is going to be accreted by the secondary, it must pass through this shock because that's a dependence domain of that's where the accretion disk form. And also when this accretion disk, if you go to the first column and also zoom in onto the first row, this accretion disk is counter-rotating with against the circumbinary disk. So there is a layer, this layer is counter-rotating, and there's angular momentum. The frictional force can transfer angular momentum.
Got it. Yep.
Yeah. So the accretion, the material inside the accretion disk is falling back because it transfers the momentum to the outer layer, which is the circumbinary disk, and the circumbinary disk gain angular momentum, and it can expand. And that's the angular momentum transfer between the accretion disk and the circumbinary disk. However, in this research, we didn't pay much attention to this mechanism, to this process, because of numerical difficulty, we cannot achieve that high precision. But that's also a future direction for the research. And so as we progress from the closed binary, which is 45 binary separation, to 5.7 AU, then we still found the circumbinary disk and also the accretion disk. However, if we continuously enlarge the binary separation to 6 AU, the second binary disk is gone. However, we also don't observe the accretion disk. And that's perhaps we predict that that's perhaps due to the accretion algorithm we implemented in the code, because the interaction between the disk and the particle, the sync particle, is much complicated than we than we thought. So the sync particle is non-physical. Its accretion is not physical. Only to some extent it can sustain the can be supportive to the physical process in this problem. And however, the accretion disk reappear in the 6.6 AU binary simulation. And although we don't know why, but I mean the 6 AU is an exception.
Right.
But in both simulation of 6 AU and 6.6 AU separation, binary separation simulation, we don't see the second binary disk. Instead, we see a spiraling outward outflow. That's a resemblance of some of the planetary nebulae that has some spiral outflow structure.
Mm-hmm.
And so this is the middle plane picture, the middle plane picture of the binary star. So we can move to another picture of the side view, the middle plane of the side view of the binary simulation we have done, and that's figure 6.
Okay.
So in this picture, we can see that the accretion disk, when it forms, they are very, very thin. They are like geometrically thin accretion disk. And this thin disk exists because we have cooling. We have cooling in the material. Mm-hmm. So if without cooling, the previous researchers have found that it's difficult to form a thin disk. Instead, you will have a fluffy ball or very fluffy disk, thick disk, or not even not a disk. But in our simulation, we found with cooling, that's considered, we consider the molecular cooling and collisional cooling. So with cooling, we can see that the disk is thin. And also the central plane, the middle plane is enhanced. The density is enhanced because of the second binary disk in the closed binary. And that's the main simulation result. And we can move to the...
I have 2 questions.
Yeah, sure.
The 2 questions. Do you have an explicit viscosity in, or is the viscosity numerical?
We don't implement any. We are solving the Euler equation, so there's no physical viscosity in our model. However, because we are using the Cartesian grid, and also, but the problem itself is accretion disk is spherical. The HB star is also spherical. So there is numerical viscosity. And that numerical viscosity can convert the kinetic energy to thermal energy. And then the thermal energy is removed by us through the cooling process. So that's a drawback of the Cartesian grid we have used. Yeah.
Okay, I'm good. Thanks.
Thanks for asking the question. And also, we can move to table 3.
Table 3.
And yeah. We have seen the main result of the simulation, but we need to analyze it. And table 3 conclude many of the facts we have sampled. So the AGB star is losing mass for 4 models. The AGB star is also losing mass at different mass loss rate, but the accretion rate can vary dramatically. From 10 to the third column shows the accretion rate, can vary from 10 to the minus 7 to 7 times 10 to the minus 9. If we use the Bondi-Hoyle accretion rate to calculate the theoretical accretion rate that can by the Bondi-Hoyle theory, and which is showed in the 1, 2, 3, 4, 5, 6, 7, the seventh column. The seventh column.
Yep.
And compare it to the third column, we can see that there is a huge difference in the closed binary. In the closed binary, the accretion rate is very different.
Yeah, order of magnitude.
Yeah. This is because the dust formation zone of these 2 closed binary is close to its inner Roche lobe. But for the wide binary, the relatively wide binary we have, the dust formation zone is inside the inner Roche lobe. And when the Roche lobe radius is close to the dust formation zone, the wind Roche lobe overflow happens, and the mass transfer can be more efficient. And also another important aspect is when the circumbinary disk form, the interaction between the circumbinary disk and the accretion disk is strong, and they can, as we thought, the friction or force between the accretion disk and the circumbinary disk can accelerate this accretion process. And we list the mechanism, we classify the mechanism of the mass transfer of these 4 models in the last column, the mechanism. The first 3, we think they are wind Roche lobe overflow, and only the last one is the Bondi-Hoyle. When it's Bondi-Hoyle accretion, when the binary is transferring mass in the Bondi-Hoyle Lyttelton accretion regime, the accretion rate drops below the Bondi-Hoyle Lyttelton accretion rate, and that's meet the theoretical point. Yeah, and we can also calculate the mass transfer efficiency by dividing the MACC, the accretion rate, by the mass loss rate. And that's how we define the mass accretion efficiency.
Right.
And that's dividing the third column by the second column, okay? And then we can move to the next, table 5. Yeah. Table 5. Above, it's above.
I missed it. Sorry, my bad.
No problem. Yeah, it's table 5. So in this table, we summarize the impact of the impact of the mass transfer on the binary evolution. It can affect the binary orbit because the mass transfer amount is huge. So by carrying out the analytical binary calculation, we find that the closed binary, their orbit are shrinking because the mass is transferring from a high mass star to a low mass secondary. And within 10 to the 6 years, which is typically the lifespan of an AGB star, within 10 to the 7 years, the shrinkage is listed or expand is listed at the right the last column of the table 5. And for the 5.4 AU binary separation, initial binary separation, its orbit can shrink 1.07 AU. And so that's only the linear prediction. If we consider that if you move closer to the star, your interaction will be stronger. And at some point, you will trigger the Roche-lobe overflow, maybe. Then that's the nonlinear evolution. In that picture, the shrinkage might be even further, even larger. So, but for the wide binary, we find that the binary separation is enlarged, is increasing because of the mass, primarily because of the mass loss, the escaped mass from the binary star, and the leftover is less massive, and their period just increase, and also the binary separation increase.
Yes.
Yeah. And
okay.
yeah. Lastly, I want to mention that the technique we use to carry out the radiation transfer is shown in Figure 8. In the appendix, the figure. This radiation transfer, this mesh is very important in the calculation because we place this mesh centered on the center of the AGB star, and the radiation is originated from the surface of the AGB star and move through this mesh. And we increase the mesh density as it moves outward because the solid angle, we want to keep the resolution high, and we shrink the solid angle. And so, yeah, that's also why we can see the shadow casted by the accretion disk is very sharp.
Got it.
Yeah.
Yeah.
It's a very sharp shadow, and it's more accurate than the maybe other method like diffusion method. Yeah.
So on those, and you get into a little bit here, it looks like in the appendix. So is that optical depth of ray trace?
Yes, it's traced back to the surface of the AGB star. Yeah.
Okay.
And I want to make specific emphasis that our model, we think our model is important for the binary simulation, binary evolution, because if you can go to the conclusion, just put on that page. We think our simulation is important for the binary simulation because usually people think that there is a phase called a model called Roche-lobe overflow, which very intense binary interaction happen. But if it's outside the Roche-lobe regime, classically the textbook will tell us that there is a Bondi-Hoyle-Littleton wind accretion, which the wind just flow out spherically, and impact, meet the secondary. However, there's this intermediate regime, which we, from the secondary, sees non-spherical wind.
Right.
That its gravity can deflect the wind from the star strongly. And also, this phenomenon is more pronounced when the dust formation zone is right at the L1 point or in the close to the inner Roche-lobe, because the subsonic feature of that layer, the secondary can impose strong effect on the atmosphere of the AGB star. And the interaction is much more enhanced just compared to the Bondi-Hoyle-Littleton accretion, and that result is presented in this research. And also, sorry,
All good.
yeah, yeah, and I think that's the thing that I want to emphasize. Yeah.
Okay, cool. I have another question. So it looked like you ran these for order 17 orbits for the closest one and about 10 orbits for the larger separation ones. And I'm curious how many core hours were invested in each one of those.
Yeah. Each of the simulation cost roughly 20 core years on the computer cluster called CIDA. CIDA is a cluster that belongs to the Compute Canada. And 20 core years is roughly equivalent to 128 cores for 2 months. Yeah, that's very expensive, I would say.
Right. So is that what you ran, 128 core?
Yeah, I ran 128 cores for 2 months for each of this simulation.
Right.
That's a very good point. I think if it will be very precious if someone can produce a table to characterize the mass transfer rate of different separation. So that can be used in some binary evolution code, more simplified code. And however, since currently this simulation are very expensive, my primary goal is, one of the primary goals is to improve the efficiency. Some technical detail is that we use the cooling, right? And in this code, in this problem, we impose cooling. Otherwise, you won't see the thin disk.
Right.
You will see a very fluffy something, not like a disk. And this cooling is sometimes very stiff. This cooling is a strong source, and its cooling time scale is much shorter than any other time scale.
Correct.
And when we meet this problem in our computation, we will shrink the time step and divide a single time step into many sub-steps.
Right.
Yeah, and that's bad for parallelized system, parallel computing. So one CPU is using a lot of time to calculate one cell, and the other CPU just being idle.
Right. It's a load balance issue.
Yeah, that's a very technical detail, but it's important, I think.
Yep.
And also another very important urgent improvement we need to face is that we should resolve the accretion disk better. As we can see, the 6AU simulation now don't have accretion disk, but that's not true. That shouldn't be true. The 6AU simulation should have accretion disk because of the angular momentum.
Yeah, there was no obvious reason why it disappeared there.
Yeah, so
and it could be a resolution issue.
One is the resolution issue, but in the paper I also mentioned that the subgrid model, the accretion subgrid model is maybe problematic for the interaction between the particle cell and the accretion disk. But a better way to resolve this is to have a spherical coordinate, spherical mesh right at the center of the secondary. But that's bad. That would be bad for the HB star because the HB star is also a spherical object, right? So
Mm-hmm.
a wild plan is that we need to resolve both. So we need to place a centric mesh, the spherical mesh at the secondary, and also place a centric mesh, spherical mesh at the around the HB star.
Right.
But there doesn't exist such mesh. So so therefore we need to separate this domain, two domains, and connect them perhaps through the SPH method. We have two subdomain and a larger domain that enclose this subdomain, spherical subdomain, and SPH fluid that travel between these two spherical subdomain. In that case, we can resolve both the secondary and the HB star. Currently, I'm not very satisfied with the resolution and the efficiency, but that's a future plan.
Awesome. Well, it sounds like the future is bright. You just laid out a couple of steps where where you're going and where the community might be going in the future. So that's great.
Yeah.
Gives you lots of stuff to work on. No, it's awesome work.
Yeah, thank you very much. And looking forward to be chatting with you soon.
Yes, and I want to thank everyone for listening in. And if you would like to reach out to Zhuo, please go ahead. You can find his email. If you're in the game, you know where to get that. We won't be putting it in the YouTube video description, but you know how to get it. So again, I want to thank everyone for listening. And Zhuo, thank you so much for describing your paper today.
Thank you. Bye.
Bye-bye. Okay.